What you're looking at is object detection, running entirely inside a browser tab. No API call, no server, no cloud. The model runs on your GPU locally right there in Chrome. And the latency, not 200 milliseconds, not 50, single-digit milliseconds because nothing leaves the device. Google announced this on July 9, 2026. It's called LiteRT.js. And it might be the most significant thing to happen to web AI since TensorFlow.js launched in 2018. Native on-device AI in the browser. Let's break it down. First, what is LiteRT? Formerly known as TensorFlow Lite, it's Google's on-device inference framework. It's the runtime behind AI on your phone, real-time translation, the pixel camera, on-device speech recognition. One model format, one runtime native hardware acceleration. The same unified stack across Android, iOS, desktop, and embedded devices. But every platform always had one gap: the web. TensorFlow.js existed, but it was a separate JavaScript implementation. Different runtime, different performance. Models didn't transfer cleanly. LiteRT.js closes that gap. It's a JavaScript binding of LiteRT, same runtime, same model format, same optimizations, now in the browser. To see why this matters, look at what web AI looked like before. TensorFlow.js was the go-to, and it works, but it had 3 pain points. 1. A performance ceiling. TensorFlow.js runs JavaScript-based kernels, not native code. You never get the full power of the GPU. 2. The conversion nightmare. Most modern models start in PyTorch. Getting one into TensorFlow.js meant a 4-step journey: PyTorch to Onyx to TensorFlow to TensorFlow.js. Every step risked precision loss, conversion failures, and debugging pain. 3. A fragmented ecosystem. Mobile ran LiteRT models, web ran TensorFlow.js, different formats, different tools, 2 pipelines for one model. LiteRT.js fixes all 3. So what is LiteRT.js? It's not a new runtime. It's the existing LiteRT runtime, the one on hundreds of millions of Android devices, compiled to WebAssembly and exposed through a JavaScript API. 3 things make it different. First, native performance. On CPU, the XNNPACK kernel runs through WebAssembly at near-native speed. But the real story is the GPU and NPU LiteRT.js surfaces 2 backends directly: the WebGPU API and the emerging WebNN API. So there are 3 execution backends: CPU via XNNPACK everywhere, WebGPU for GPU acceleration, and WebNN targeting NPUs, still experimental. And the numbers are big. For real-time tasks, WebGPU or WebNN deliver a 5 to 60 times speedup over CPU execution. Second, one model format, the same tflite everywhere. Your Android team's model just works in the browser. And third, it automatically inherits every future LiteRT optimization. One of the most practical changes is model conversion. The old TensorFlow.js path was 4 steps: PyTorch, Onyx, TensorFlow, TensorFlow.js. 4 tools, 4 chances for numerical precision bugs. A bad Onyx export could silently corrupt your outputs. The new path, 1 step. A single import LiteRT torch takes you straight from PyTorch to a tflite file, ready for browser, Android, iOS, and desktop. and it drops into existing TensorFlow.js pipelines. Keep your pre- and post-processing code. You only swap the model inference step. Migration risk is minimal. LiteRT.js handles classical models, detection, classification, audio. But Google shipped a second layer on top, LiteRT-LM.js. It's a JavaScript API that runs full large language models in the browser. The models it supports today, Gemma 4, in the E2B and E4B variants, tuned for the edge. Here's a complete in-browser chat app. Import the engine, load Gemma 4 from Hugging Face and stream the response. That's it, no backend, no API key, no rate limits, no server costs. Powered by WebGPU, it runs entirely client-side, serverless, private, and free per inference. One honest caveat. The browser API is an early preview, text in, text out, Gemma 4 only. Tool calling and agentic features live in native LiteRT-LM today. The web API is just getting started, but the direction is clear. Zoom out. Why does running AI in the browser actually matter? 3 reasons: privacy, cost, and latency. Privacy. Inference runs locally, so your user's data never hits a server. For healthcare, legal, and note-taking apps, that's the answer. Cost. Every cloud AI call costs money. On-device inference has zero marginal cost. Once the model is cached, every run is free. Latency. A cloud round trip adds 100 to 500 milliseconds. On-device, at up to 60 times CPU speed, real-time actually means real-time. This unlocks private document analysis, real-time camera detection, offline AI, and web apps with zero API cost. This is a day one announcement, so let's be honest about where things stand. Available now. The core runtime on NPM and CDN, the CPU backend everywhere, and the WebGPU backend in Chrome and Chromium browsers. Existing tflite models from Kaggle and Hugging Face work today, inside your existing TensorFlow.js pipelines. Experimental or coming. The WebNN backend for NPUs still needs browser flags and isn't generally available. And Firefox and Safari support varies. WebGPU isn't everywhere yet. Getting started is 2 lines. npm install the core package, then load LiteRT with the WebAssembly path. Load your model and run. So to recap, LiteRT.js, announced July 9, 2026, is Google's JavaScript binding of LiteRT, bringing native on-device AI to the browser. It solves what TensorFlow.js couldn't: native performance through WebAssembly, one-step PyTorch to tflite conversion, and one runtime across mobile, desktop, and web. 3 backends: CPU, WebGPU, and WebNN, and on top, LiteRT-LM.js runs Gemma 4 locally, streaming, serverless, private, and free. The gap between native and web AI just got a lot smaller. If you build anything AI on the web, this is worth trying today. The NPM package and CDN are live. Drop a comment on what you'd build with it. See you in the next one.